It's my pleasure to share with you some of our work about the theory of weak supervision and the software that this theory enables. Weak supervision is an area that has exploded over the past few years. Biased by my own work, my hope in this talk is to share some practical use cases and to give you a taste of the underlying theory. There's a lot going on in this space, and I've tried to put pointers throughout the talk if you're interested. In the last few years, the practice of machine learning has changed dramatically. For many applications, ML has three ingredients: a model, some training data, and hardware. With the advent of deep learning and great software frameworks like PyTorch and TensorFlow, state-of-the-art machine learning models are easy to download and use. With the rise of cloud service provider, folks have access to vast arrays of hardware resources. So state-of-the-art models and hardware are available like never before. However, training data is not. In some ways, this is not surprising. In a real sense, training data is how one defines their ML application. It's really how you program your task or application. So it's not surprising that you can't readily download training data customized for your application. So to make it easier to build ML applications, we'd like to make it dramatically easier to create training data. From the machine learning side, we want to make training data construction a first-class machine learning citizen. On the system side, we take inspiration from classical software development and think about how to make the process of creating training data more like the process of creating software. Now, when I first started talking about programming by supervision, this felt like heresy to some of my ML friends, and I totally get it. When I teach supervised machine learning, we begin the lecture with a set of data points and their labels. We never say where those points or those labels come from. In fact, most ML students are left with the impression that supervision drops from the sky directly from God herself. Now I wish building ML systems was like hanging out with Beyonce, but anyone who has built ML systems knows that the process is decidedly less glamorous. It's more like living in the sewers. Specifically, the process of building training data is a dirty, messy process. Often practitioners take multiple streams of messy data and combine them to make a training set. These data sources have unclear quality, and this process is largely manual and time-consuming. Our goal in this line of work is to understand this process and hopefully make it a little less awful. We haven't solved these problems, but what we're trying to do is provide a mathematical and system software structure to help support this messy process. While we've developed some exciting theory and maybe even some systems that you might have used, it's important to emphasize that we're much closer to the beginning of this research program than to its end. Although we're near the beginning of this research program, I'd argue that already understanding supervision has been where a lot of the action is in the machine learning community. In particular, what I'm going to argue is that modeling differences are vastly overrated, while supervision differences are often underrated. To substantiate this, let's look at some real examples and benchmarks. Our group likes to work on applications to hold our feet to the fire. This work was described in Radiology, which is the flagship clinical journal for its namesake area. The folks in ties are physicians, and the others are computer scientists. This project was led by Jared Dunman at the right. Jared did a ton of work in this application. He spent more than a year assembling labels that were validated by clinicians. He evaluated the effect of label quality, and more importantly, he spent time hanging out with domain experts, understanding the challenges of applying ML in these spaces. I'd recommend you check out his work about the efficacy of machine learning in these settings. For example, his work on hidden stratification. One task we discussed was triaging radiographs by severity. In this study, model choice is not critical. Here are the results of various different models. DenseNet does great. It's a fantastic model. Other popular deep models also do well. However, the model at the top that's listed there is actually a bag of visual features model. This is a model you could have comfortably trained in the early 2000s, and the difference is only a couple of points. This is something we've seen again and again in real applications, that the label quality and quantity often matter much more than the details of the model itself. Now, the spirit of this statement is true in benchmarks as well. In CFAR 100, if you remove the important augmentation step, you lose 13 points of score. In contrast, the difference between top-performing models are now in the tenths of points. Now, modeling is important, but its importance relative to label quality may be less than you expect. Yet while we have a lot of research about how to improve our modeling, we have dramatically less research about how to improve label quality. Supervision is also key to pushing the state-of-the-art in quality in benchmarks like ImageNet, two things that started with folks in our lab that I'm particularly proud of here. Alex and Henry had this great paper in NeurIPS 2017, in which they were the first to propose that you can learn how to compose your data augmentation policies. Google picked this work up and extended it in a really exciting direction in AutoAugment and RandAugment, and they used it to set a new state-of-the-art on ImageNet. Sharon Lee, a postdoc in our lab who is now headed to Wisconsin as faculty, did a really exciting piece of work at Facebook. With her collaborators, she trained an image model on a massive corpus of images and hashtags. In addition to attaining high quality and setting a state-of-the-art at the time, it turns out that her models may actually be more robust than other models to distribution shift, as shown in some recent work by Ludwig Schmidt and his collaborators. We've been doing a bunch of work on the theory of augmentation, and unfortunately I don't have time to share that with you today in detail, but I wanted to highlight a blog post that Sharon led that talked about some of the recent progress from our group and others in data augmentation. One particular nugget in there is some recent work on uncertainty-based sampling for data augmentation that actually sets a new state-of-the-art on a couple of different image benchmarks, and moreover, it has a clean theoretical explanation for when some augmentations work, including notoriously difficult things to understand, like mix-up. Hongyang Zheng and Sen Wu led this work. Hongyang's going to go be a faculty at Northeastern next year. I highly recommend you follow both of their works. So hopefully at this point, you kind of agree that training in data is an important bottleneck in machine learning, and that there may be something for machine learning people to do here. So what would we like to improve about the training data collection process? Well, if I think about the way that we collect training data right now, I'm struck by the fact that it's kind of slow, expensive, and static. And let me unpack this for you in a little more detail in the next slide. Manual labels are slow. Your first label takes as much time as your last label. There's no economy of scale. Humans don't get appreciably faster over time. Manual labeling can also be quite expensive. This past year, we had a Nature Comms paper with cardiologists in which we were looking for events that were rare in video. The background incidence was somewhere around 1%. Having highly trained users look through 100 videos to find a single positive example would have been exorbitantly expensive. Perhaps more subtly, manual labels are static. Suppose you've labeled customer reviews as having positive or negative sentiment. However, you realize you also want neutral in your application. What option do you have? Unfortunately, you have to manually relabel the entire set. Now, we're not able to perfectly solve any of these problems. However, we're going to make a start at them with a formal framework that's based on programmatic labeling. The idea is that you'll write little programs that encapsulate how to label. Our hope is that these programmatic labels will be fast. In particular, we'll show some examples in which people have labeled their data in person hours instead of person years. They'll be cheap because they run at machine speed, not human speed, when they have to deal with data. Perhaps most conceptually exciting, they're also dynamic. We're going to treat programmatic labeling functions as code, and so you can refactor them and really treat them as a first-class software citizen. Now, there is a trade-off. We get all this good stuff, but we're going to have to tolerate labels that are potentially much lower quality. Worse, we don't know how bad they are. And a key statistical challenge is to learn how accurate these programmatic labels are. We'll describe our technical progress there soon. I want to be really clear here that the idea of using lower quality data for training machine learning models has a really long history. Some of my favorites are things like using pattern matching to generate heuristic training sets that goes back to Marty Hurst's groundbreaking work in the 90s. More recent stuff like using distant supervision for relation extraction in the Jurafsky and Mintz paper in 2009 are also super cool and exciting ideas. And there are many, many more. Now, in essence, we were inspired by all this practical success, and we wanted to put these techniques on a firmer statistical footing. In particular, we observed ways that forms of weak supervision are often used in ad hoc or isolated ways. Practitioners would use only one of these methods and not get the full power of using them all together. Our goal was to enable people to use all of these methods when they faced challenging machine learning problems. So this is why we built Snorkel. The key idea is to take all of these different, noisy, highly correlated sources of supervision and denoise them. In particular, we'll try to produce estimates of how much we trust each training point. One key technical challenge is to estimate the quality of those training points without using any labeled data. Now this work is due to some really amazing folks, and two in particular I want to call out here are Stephen Bach, now a professor at Brown, and Alex Ratner, who's going to be a professor at the University of Washington next year. Check out all of their work at snorkel.org and pay special attention to those two who are entering academia. Okay, so let's look at an example. We have a snippet of text in which we're looking to classify mentions as either a person or a hospital. Of course, we can do more complex tasks, but I want to illustrate how this is done concretely in Snorkel. And our idea is to look at labeling data for this using these weak supervision approaches that we've seen on the last slide. Now the key unit of Snorkel are called labeling functions. Consider this highlighted mention of St. Francis, which corresponds to a hospital. The first labeling function wraps an existing model, and it incorrectly votes person. The second labeling function uses the first labeling function, the same classifier, but does a little bit of additional processing and also votes person. Pretty clearly, this second labeling function is correlated with the first function. The third function actually just uses the distance supervision heuristic. It looks up St. Francis in its database of hospital names and correctly votes hospital. What I intend to illustrate here is that these sources are noisy. We don't assume they're perfectly accurate. They can conflict with one another, and in fact, they can be correlated. And we want to model all of these elements as a statistical learning and inference problem. So how does this work in Snorkel? Well, the user writes down these labeling functions. Then we view the errors that are produced by these labeling functions as coming from some distribution characterized by a graphical model. For experts, each source, not each vote, is a node in this graph. In this graphical model, the ground truth variable is latent. We don't observe it. And the idea is to estimate the parameters of this model without direct access to the ground truth. In turn, this model is used to create training data by forward inference. And here we assign to each point a confidence score based on how all of the sources voted on that particular point. In turn, this probabilistic training data is then fed to your favorite deep learning model. The key idea is that the probabilistic inference on training carries out our confidence computation, and importantly, no hand-labeled data is necessary. Of course, if you have it, you can use it, but that's not kind of the art of the project that we're after. Now maybe this sounds like a crazy idea to you. Some of the smartest people I know thought it sounded like a crazy idea, but they were my students and they made it real. Perhaps surprisingly, Snorkel is actually used at big companies, small companies, by scientists, governments, and in many more places. This is an incomplete list of the folks that we know that are using it. To be clear, this doesn't suggest that Snorkel is the ultimately right solution. What it really suggests to me is that we fill a key gap in the machine learning pipeline, and we're just at the early stages of this new type of system. One set of collaborators to whom we owe a great deal are the folks at Google Ads. Google has collaborated with us on a series of exciting projects. One of those is called Snorkel Drybell, which is their internal version of Snorkel. In this Sigmon 2019 paper, they described how they use Snorkel Drybell with all the organizational resources that they have to quickly, weekly supervise new models for production. The main idea was to categorize all of these different sources that are out there and bring them to bear on the problems that they had. I'd also like to highlight two other projects. One is Overton, a system in production at Apple that I wrote with some collaborators. I'll share data from this system in a second. Also, the Gmail folks were very generous in their recent talk to describe how their new architecture very closely maps to Snorkel. It's super exciting to see folks use some of these ideas. Anecdotally, we hear from folks who use weak supervision a lot in production, and this chart is pretty exciting for me. It shows two things. The first is that folks do actually get error reduction when they use weak supervision over previous approaches. The quality does improve. But also, if you look at the amount of weak supervision, it's actually a substantial fraction of the training sets. So it's really exciting to see that this change in software development is actually happening. I want to also plug a little bit that it's beyond industry, that these are things that are used by scientific collaborators as well. There's been a whole host of use of weak supervision in science and medicine in our lab and in other labs around the world, and we're trying to highlight that on a recent blog post. There's some really exciting work in this space. The Ludwig system is one of my favorites. It's super exciting and I highly encourage you to check it out. It describes how we can go to higher levels of abstraction to very rapidly build machine learning models. They don't focus on programming supervision, but they're also what looks like a key ingredient in the space of new software tools. Andrej Karpathy coined the term Software 2.0 in this blog post, and he articulated how he viewed software as changing. So I think there's really a change in how we build software that's going on, enabled by many of the really exciting tools that are built up around us. Okay folks, let's look at some math. This section is credit to Alex Ratner and Fred Sala, who are really amazing folks. These results are spread out over several papers as we refine the theory and the model. The key question is, how can we do any of these learning procedures without hand-labeled data? Let's take a closer look. The key idea is to model the production of training data as a generative process. Recall those labeling functions we saw earlier. For each function, we imagine that there is a hidden accuracy parameter that corresponds to that data source. With some probability, the source gets that training point wrong. There's also potentially correlations among the sources, which is graphically illustrated here. We don't observe y, the ground truth, and so the entire technical challenge is how to learn the parameters of this model, the accuracies and the correlations, without direct access to y. The key insight is that by modeling sources, we can see each source vote many, many times on each data point. While we can't see how often those sources disagree with the ground truth, which would make our job of estimating the accuracies straightforward, we do get to see how often they agree with each other or disagree, and we can count that up and estimate it. So we need a little math to describe this. What we'll do is measure the expected agreement rates of all those labeling functions and form a covariance matrix, which is illustrated here. I've also added in a column y and a row y, which corresponds to the covariance with the ground truth. We can't observe that portion of the y. We can only observe the interactions among the labeling functions. If we could observe the expected value of lambda 1 and y, well then we'd be done. That's approximately the accuracy. So to recover the rest of the matrix, we're going to use a couple of insights. It turns out that there's a nice connection between the inverse covariance matrix and the structure of the graphical model. For now, assume we know the graphical structure. It turns out that we can also learn the structure, so this is really just for exposition. Roughly speaking, we know that in the inverse covariance matrix, there is a 0 whenever an edge is absent in the graphical model. How are we going to use this? Well, first we need to do a little bit of manipulation to put it in the right form. We observe we can write this inverse, which we cannot directly measure, into two terms. One is a covariance metric that we can actually observe, sigma sub 0 inverse. And a second term, which consists of a bunch of rank 1 terms. The z here is not mysterious. It's almost a direct function of the accuracies. It just requires a little bit of algebra to write it out precisely. Now, whenever an edge is absent in the graph, we get a 0 on that left-hand side. This means that we can write an equation in terms of the parameters we want to solve for, the zi's and the zij's, solely in terms of a quantity we observed, that observed overlap matrix. So how many such examples do we need? Well, roughly we need enough zeros to recover all the parameters. That means roughly a 0 in each row or column. This corresponds to constraints on the graphical model underneath the covers that suggest that not all labeling functions are very highly correlated. A few technical comments are worth making. First, notice that there's a symmetry here between z and minus z. They're both indistinguishable as solutions. This actually makes sense, as we can't tell if all the labeling functions are aligned with the ground truth or exactly aligned with its negation. In our applications, people are constructing these labeling functions, and so it seems justified to make a mild assumption, such as, on average, the labeling functions are more correlated with the ground truth than not. But this is important to be able to break the symmetry that's inherent in the model. When zi is equal to 0, this implies that the labeling function has accuracy 0.5. That is, it's flipping a random coin. In this situation, we should get no information, and this gives some insight that your theorem should actually scale proportional to the distance between zi and absolute noise. And in fact, we worked really hard to get the right scaling in terms of that quantity. Finally, as I briefly alluded to, it turns out that the right measure of complexity in the sample here isn't rank, but there's a nice tool called effective rank that gets us exactly the right scaling. Somewhat surprisingly, this tool also allows us to improve the standard supervised structure learning rates as well for some select graphs. After producing all of those estimates for each data point of how accurate it is, we then feed that data to your favorite deep learning model. For experts, this amounts to basically taking off the last layer of your model and replacing it with something that allows softer labels. This is something that we've been able to do on a huge range of models, from text to image to video, effectively every deep learning model that we've encountered. One natural question to ask from a theoretical perspective is how valuable is weakly supervised data compared to traditional supervised data? Roughly what's stated here is that under pretty mild statistical assumptions, weakly supervised data is no worse than traditional supervised data. In particular, we can derive an explicit constant, like 2 or 4 in some settings, that says that we only need a factor of 2 or 4 more weakly supervised data to achieve the same kind of generalization that you would expect from traditional supervised data. However, producing the weakly supervised data may be able to happen with order of magnitude fewer resources than were used to produce the same amount of supervised data. Here are some standard results where we show that over some benchmark results, using weakly supervised data actually improves over traditional supervision. However, one of the things we're more excited about is that this is something that people are using on real applications today. I want to mention something that's really conceptually important to me, which is that weak supervision can change how you iterate and how you build models. To substantiate this, let's go back to our friends, the physicians. Here's the problem they were looking at. They wanted to train an image model for triage, so they took the standard fully supervised approach, and they spent person months labeling a host of data and got an AUC of 0.88. Not so bad. This looked valuable to them, so then they decided to spend person years on data, and they improved their AUC by another 7 points to get the line that's shown here. Now we decided to attack this from a weak supervision angle. So here, the idea was to create an image classifier, but instead of using labels that were constructed by experts looking at the images, we decided to use the reports. So we would extract features that were important from the reports and use those to construct weak labels for the images. Now, importantly, this two-step process of weak supervision was critical here. We wanted a classifier that worked just on the image. It couldn't use the report because in triaging, the report isn't even written yet. So we couldn't use the features at test time from the actual text, just to produce this probabilistic training set. Now, Jared, who I mentioned earlier, actually went over there and hung out with these folks and spent about 8 hours understanding from them how they were able to classify an image and what was important to look for in the reports. And he wrote down about 20 labeling functions, ran it through Snorkel, and in about a day or so actually had a model. These are his results. Now the AUC is slightly lower than the fully supervised case, but one of the things that's really important to note is that it only took person days. Imagine if instead of spending those person years on this project or person months to get an initial model, we could have simply started with the Snorkel model. Those are some of the cases that we're seeing in industry and why we think it's so interesting that these weak supervision approaches could potentially change how we go about the process of building machine learning software. There is a truly staggering amount of related work, and there's no way that I could do any of it justice. We've been inspired by a tremendous amount of work in this area over the past couple of years. One of the things that we've done is try to create a blog post where we start to summarize and understand the different approaches to weak supervision that are going on in the literature. If you have information or new work that you think we should be aware of, or some classics that we've missed, please don't hesitate to reach out and send us a note. We really enjoy it. Now allow me to briefly describe some of our future work. As I mentioned, we want to draw parallels between classical software development and machine learning. This is an admittedly imperfect analogy, but we found it helpful to explain our vision. You can think about the traditional zeros and ones of label data in machine learning as analogous to machine languages. One layer up the stack are assemblers, which are quick ways of specifying entire groups of bits. We can kind of view the work that we've described in Snorkel as just this first layer of abstraction over binary code. However, these labeling functions are just the basics. Modern software is composed out of existing libraries. In a pair of papers, we started to examine how composition affects the type of analysis we described in this talk. For example, analyzing source code may reveal dependencies among labeling functions that are difficult to learn from data alone. One can go even higher level. In declarative languages like SQL, you say what you want, not how to get it. In an ACL paper, we described how one could take statements in pure natural language and compile them into labeling functions using semantic parsers. As with traditional high-level languages, this allowed folks who don't normally write code to be able to participate. For example, folks at a neuroscience startup who didn't know Python were still able to productively write labeling functions for their applications using this interface. Finally, what we're working on now is at the highest layer of the software stack. Here, we observe the behavior of machine learning users by instrumenting their software. These are like APIs for learning that are embedded into your existing software environment. So the analogy is certainly imperfect, but I hope it illustrates why we're excited. There do appear to be some actual technical consequences for Software 2.0, and it's more than just a fun buzzword. Of course, my view of the future doesn't matter all that much. The folks who do the real work and push things forward are my students and postdocs. They've written a blog post that I highly encourage you to check out about the lessons they learned building some of these Software 2.0 systems and the future directions that they find most exciting. It's been an absolute pleasure to share some of our work with you. In particular, I discussed Snorkel, which was a framework for rapidly creating training sets that's thankfully been used in a number of applications. I described a little bit around the technical nuggets that are underneath such systems. For example, estimating the quality and accuracy of various data sources used in the training and supervision process. We're really excited by how programming is potentially changed by these new systems, and that's a area of very active research. To follow up, check out snorkel.org or any of our group's blog posts. Thank you so much for your time and attention.